Hi there, I'm Anton, and I'm participating in a project called Project Forskerspirer. It's a national Danish talent development scheme for further education college students like me. It's designed for anyone with a passion for research. So over the next year, my project will be focusing on designing and prototyping an RF transmit coil for Carbon-13 MRI. This series of videos will function as kind of like a visualization of my learning process. In this first video, I'll explain what Project Forskerspirer actually is, why I chose this topic, and what I've done so far. Project Forskerspirer was initiated in 1997 by the Danish Ministry of Science and the Ministry of Education. It's supported and maintained by the University of Copenhagen and Aarhus. I signed up for the project because I'm genuinely drawn to R&D, research and development, solving complex problems with physics, electronics, and engineering. I don't just want to learn theory, I want to learn to apply it. And Forskerspirer kind of gives me the structure to go from question to hypothesis, to design, and to get results with real researchers as mentors. As a participant of Project Forskerspirer, I get access to seminars, tools, and research guidance. I choose a topic within the humanities, social studies, health, or in my case, natural sciences. The official plan is then to find a researcher and submit a research synopsis by October, including how one would research the topic if they had the resources for it. I, however, was lucky enough to find a researcher with immense dedication. Already in the first mail I received from them, they requested my full dedication and told me I would be working on state-of-the-art problems. After meeting him physically at the Technical University of Denmark, DTU, he offered me to work with him on designing a low-pass birdcage transmit coil for metabolic imaging with Carbon-13 at 3 Tesla MRI scanners. I, of course, said yes to this extraordinary opportunity. Unlike hydrogen, Carbon-13 can trace metabolic processes, like how cancer cells consume glucose or how the heart burns energy. But clinical MRIs are built for protons at around 127.7 MHz. Carbon-13 resonates at 32.13 MHz at 3 Tesla. So my project is to design a coil specifically tuned to that frequency. In short, it's like a perfect intersection between applied physics, electrical engineering, and the potential for actual real impact. Exactly the kind of interdisciplinary engineering I want to work on. If we can successfully integrate a Carbon-13 MRI transmit coil in hospitals, we can enable real-time metabolic imaging. That means earlier diagnosis for diseases like cancer, liver disorders, heart conditions, diabetes, and it also means improved patient care. So far, my project has been going on in 3 phases. The first phase was finding mentors. I reached out to 7 researchers working in MRI-related areas through university lab pages, DOAJ, and by structuring my search with queries. I used search schemas to refine my search, studied their publications, and formulated questions that showed I've actually done my homework. Some researchers replied, including my main contact, whom I'm doing this project with almost on a weekly basis. When I was not meeting up with researchers or writing emails, I would be studying math, physics, and engineering intensively. MRI is a pretty complicated topic. To understand it, you need a deep understanding of electromagnetics, math, electronics, introductory quantum mechanics, and a lot of engineering design. Some of the topics I've covered so far are geometry, nuclear magnetic resonance spectroscopy, a lot of electromagnetism, basic electronics, algebra 2, trigonometry, and a whole lot of birdcage coil designs. I'm a big fan of Scott Young's ultra-learning method, which despite its clickbaity name, is backed up by science. Using it, I've been able to study all this effectively, and this is still ongoing. Finally, I started learning how to use CST Studio Suite for electromagnetic simulation. I built a bunch of different projects to learn how to use it, and I'll soon be able to simulate and design the birdcage coil I'll be making in real life. So far, my S1.1 parameters, which tell me how much of a signal is reflected back, are a little off. What you see here is a matrix transformation of said S1.1 parameters into this graph over impedance as a function of the frequency. Those spikes you see there are supposed to be at 298.2 megahertz, but so far I can only get them to hit around 200 megahertz. Some problems I've had with CST Studio Suite is the fact that there's almost no learning resources for it online. I have been able to manage, though, through both help from my mentor and through trial and error. So that's where the project stands right now. Over the next few months, I'll be documenting the design process, testing setups, and I'll be telling you about some of the challenges I face as I try to translate simulations into real-world function. Thank you for watching.